going to study Science of Class 9th, chapter number 9th, Force and Law of Motion. In last video, we have read about first law of motion, law of inertia. Now we are going to study about second law of motion. And we already talked about momentum. So what is momentum? P is equal to, momentum is denoted by P. P is equal to mass into velocity. So it can be written as P is equal to m into v. This is momentum. And the definition of momentum: momentum is physical quantity that is measure of the impact of force on a body of mass m moving velocity v, defined as the product of its mass and velocity. P is equal to m into v. This is a physical quantity. We already talked about that. Now we are going to study about second law of motion. Newton's second law of motion states the rate of change of momentum is directly proportional to applied unbalanced force and take place in same direction as the applied force. You have to note the second law of motion. Newton's second law of motion states that the rate of change of momentum is directly proportional to applied unbalanced force and take place in same direction as the applied force. So we can understand this by this. Suppose here we have a object. Suppose here this is a object and it is moving with velocity v. Initial velocity is u and final velocity, and then we applied a force F in this direction. Applied force F. So velocity increased from u to v. Final velocity is equal to v. So suppose as you can see here, suppose an object of mass m is moving in a straight line with the initial velocity u. It moved with uniform acceleration a and achieve final velocity v. Here it moved with uniform acceleration a, and here the rate of change of momentum is directly proportional to applied unbalanced force. Here it is called unbalanced force, this is unbalanced force, and here it is called uniform acceleration. So you know that F is equal to m into a. If we applied a force, then the body of mass m will accelerate with a. So this is same, it move with uniform acceleration a and achieve final velocity v in time t. So here the rate of change of momentum, so suppose initial momentum is equal to p1 is equal to m into u, initial velocity. Final momentum is equal to p2 is equal to m into v. Here the rate of change of momentum means rate of change of momentum. So rate of change of momentum. So first we find the change of momentum. So change of momentum delta p, change in momentum delta P is equal to P2 minus P1 is equal to mv minus mu is equal to m comma v minus u. This is change of momentum. Sorry, this is change of momentum. Then rate of change of momentum with respect to time. So yeah, you can write with respect to time, delta P upon delta T, or it can be written as dP upon dt. And this, now this implies dP upon dt, and we here comma here dP is equal to m v minus u. We put the value of dP here. This implies d, or equal, just equal, d bracket m into this is upon dt. Okay, here equal to, now we, this is m, so this will be m, and this is change, and we know that this is like dv minus u upon dt, and this is equation 1. We know that from first equation of motion, v is equal to u plus at, so v minus u upon t is equal to a. So we put the, this is v minus u upon t, we put the value of this here. So rate of change of momentum is equal to dP upon dt is equal to m into dA. And what is this? This is mass, this is acceleration. Okay, so this will be force. Okay, so this will be like dA into cross m. This will be force, or simply you can write this, forget about this d, and just simply do this, rate of change of momentum p upon t. Just do it like p upon t. If you are confused, you can do it like this here, rate of change of momentum, rate of change of momentum p upon t. Okay, p, rate of change of momentum delta p, so is equal to m into v minus u upon t, or v minus u upon t is equal to a, m into a. M into a is equal to f, so we can say that delta p upon t is equal to f. Okay, so we can write here, now dP upon dt is equal to df. This is rate of change of momentum. If you want to write this, you can write this on your notebook. And also this statement: Newton's second law of motion states that the rate of change of momentum is directly proportional to applied unbalanced force and take place in same direction as the applied force. So you can see here the rate of change of momentum. Rate of change of momentum is directly proportional to or equal to unbalanced force df, unbalanced force, and take place in same direction as the force applied. If we applied a force in this direction, as you can see, if we applied a force in this direction, so the change of momentum will be in this direction. Okay, now definition of force. On the basis of above equation, we can say that force is an effort that produces an acceleration A in the body of mass m. It is the product of mass of body and acceleration produced in it. As you can see here F, this is rate of change of momentum m bracket v minus u upon t, and here he put the value of dp, delta p upon delta t is equal to f. He put the value of delta p upon delta t is equal to f, and he proved f is equal to m into a. And here we take f is equal to, here as you can see here we take f is equal to, here f is equal to m into a, and we prove dp upon dt is equal to df. Here it take dp is equal to dp is equal to delta f and proof f is equal to ma. Here we proved, here we took f is equal to ma and proved dp upon dt. Okay, both are same. So if you want to write down this, so you can also write this, or you can write down this. Here you can see f proportional to m into v minus u upon t. Now definition of force. On the basis of above equation, we can say that force is an effort that produces an acceleration A in the body mass m. It is a product of mass of the body and the acceleration produced in it. Unit of force. So you know that here F is equal to mass into acceleration. So unit of mass is kg. Unit of acceleration meter per second square. So unit of force is kilogram meter per second square. Kilogram meter. So unit of force. From the formula F is equal to m, we know that SI unit of mass is kg and acceleration is meter per second. So SI unit of force is kilogram meter per second square. As we know, F is equal to m into, okay, and it can be written as Newton. 1 Newton force is force which produces an acceleration of 1 meter per second square in a body of mass 1 kg. Principal application of second law of motion. So, practical application of second law of motion. There are many applications of Newton's second law in our day to daily life. Some examples are given here. When a fielder of cricket match, you can see when a cricket in a cricket match, when a player take a catch, he move his arm up, like up to down. So the force So you can understand this like this. If the mass of ball is equal to m, okay, and the ball is coming with the velocity v, when the player take the catch, the velocity of ball is u. When he take when he takes catch. So you can see, when a fielder in a cricket match take a catch, he move his arms back. This is because if he tried to stop the fast moving ball suddenly, then the after speed decrease to zero in very short time. Thus the rate of change of momentum of ball will be large. Consequently, the impact of ball, fast moving ball, would also be very high. A large amount of force is required to stop the ball and fielder may get injured. On the other hand, if the fielder stop the ball gradually by moving its arm back, then the velocity decrease gradually in longer interval of time. Hence, the change of momentum would be very low. As a result, the force extended by ball on the hand decrease and the fielder does not get injured. The value of force, as you can see from last second law of motion, delta p upon delta t is equal to, sorry, delta p upon delta t is equal to delta f if the value of delta t is t1 and t2 and t1 is greater less than T2, so F1 will high and F2 will low. If the denominator, if divider is higher, so net amount is lower, and if the divider is lesser, so net amount is higher. Okay, if the value of t1, if the value of delta t is less, if delta t is less, f will high, or if delta t is high, means delta f will low. Okay, so net force, if the time interval is large, so net force is low. If the time interval is less, if we just impact the ball and he catches, so there are more force and he get injured. If he moves his arm down, so interval is high, so force is less and he does not get injured. In high jump competition, the attached ball either on a consecutive pad or sandbag. This is to increase the time of athlete's fall to stop after making the jump. Same example, here he taking catch and move his arm, and in this example the athletes jump in a bad crunch bag or sandbag, so the time of fall will be increased, so the change of momentum will be less. Now we will study about third law of motion. It called be law of action and reaction. This law can be explained by this. Suppose this is our object. Let me do it in rest. Yeah, this is in rest. This is our object, and this is in rest. Okay, we this is now I am explaining three law in a way. Row. This is first law. This is a body which is in rest and it is not moving until we are forcing it. Now we are forcing it and it is moving. So this is first law. Okay, now it is continue moving. We apply the force and it goes move. So this is law of inertia. Okay, and now third law of motion. Third law of motion, action reaction can be explained this. Suppose this is a rubber. Okay, we elongate it and we applied a force along it, and now in this position. Now we leave from here. Now it return to its original shape. This is action and this is reaction. Okay, this is action, this is reaction. He stored up, and this can be explained like this. Suppose here we elongate it, now we posed it, and now we can fire anything from it. Okay, and the example here you can see in this figure, a boy has, as you can see in this figure, the sailor has a paddle in his hand and he moved this paddle backward. Then the boat moved forward. So if he applied force in backward direction, so water pushes him in forward direction. Okay, and this is the example, not definition. When an object extract a force on another object, the second object internally exert a force back on first. These two forces are always equal in magnitude but opposite in direction. Okay, if we apply the force in downward direction, so this surface will exert a same force. Magnitude is same, but the direction of this force will be opposite, like this. This is surface. We applied a force in this surface. Okay, so this surface exert a force in upward direction in this point. At this point, this surface will exert a force same magnitude force, but the direction is opposite. This is called action, this is action, and this is reaction. If we apply the force and there are some reaction, this is called action reaction force or law. Now we will talk about example of third law of motion, action reaction. Here you can saw a gun. When we fire a gun, a bullet from a gun, so gun recoils back. This is the law of action reaction. Now we are going to study about conservation of momentum. From Newton's third law of motion, we know that whenever a force is applied on a body, there will be an equal and opposite reaction. Action and reaction force result a change in the velocity of both, and body in turn change the momentum of this body. Newton's second and third law of motion lead us to very important law of mechanics, the law of conservation of momentum. Or this can be called the principle of conservation of momentum. Here you can, now first we read this statement. If a group of body are exerting force on each other, is that interacting with each other, their total amount remain conserved before and after the interaction, provided there is no external force acting on them. Suppose there are two balls, as you can see in this figure. There are two balls. This is first ball M1, this is second ball. So This is ball, second ball, mass mb, velocity vb. This is first ball, mass ma, and velocity ua. Okay, initial stage. Now this is middle stage and this is final stage. Final and middle. So what happened, this and the value of ua is higher than ub. Here condition, we write down the conditions here. ua is greater than ub, ma is not, and ua is not equal to ub, ma is not equal to mb. Okay, before collision, collision, after collision, initial stage, middle stage, final stage. Okay, this is before collision. In stage of collision, both are same. Now the total mass is m1 and m2. At stage of collision, mass is equal to ma plus mb, and velocity is equal to v. After collision, velocity after collision, here mass is same or mass could be different. If it breaks, so mass could be different, or if it is not breaking, so mass is same, but the velocity will change or could be same depend on the condition. So according to second law of Newton, now two ball A and B are moving. No, masses A and NB are moving in the same direction with initial velocity UA and UB. Let's UA greater than UB and two bodies make a direct collision. Let us assume that after collision they continue moving in the same direction. Means if they are moving in this direction, after collision they will also move in this direction. Okay, assume that the, here we assuming collision they moving in same direction, so we assume they are moving in this direction, and after collision that is also moving in this direction. Okay, and assume that collision occur a very short time interval t second. The collision timing of collision is very short. This is t, or it can be delta t, anything. During collision, the ball A exert a force AB on ball B, and the ball B exert a force BA on ball A. As you can see here, in this figure, at the condition of collision, this ball exert a force FAB in this direction on ball B, and ball B exert a force on ball A. The quantity of force is FBA. Time interval is delta t or t, very short. After collision, now during after collision, due to this action and reaction force, the velocity of A and B get changed. Suppose VA and VB are the velocity of two ball A and B respectively after the collision. Okay, according to Newton's second law of motion, we know that F is equal to ma. Therefore, force exerted by ball A on ball B will be FAB is equal to ma AA. This is mass, this is acceleration of ball A. So is from velocity relationship, v is equal to u plus at. This is first law of motion. A is equal to v minus u upon t for ball is, so va or aa is equal to va minus ua upon t. Therefore fab is equal to m va minus ua upon d or fa. Okay, in the similar, the force exerted by ball b, same thing, mb minus mb ub upon t. Now, according to third law of motion, the action and reaction force are similar in magnitude, but direction is opposite. So here they are moving in same direction, and here the magnitude is same, but the opposite in direction. So we take minus FAB is equal to minus FBA. Now put the value of AB and BA here. MAVA minus MAUA upon T is equal minus MBVB minus MBUB upon T. T cancel. MAVA minus MAUA is equal to minus MBVB plus MBVB. Now we take this to this direction and this side, and this side. So we can write this MAUA plus MBUB means initial condition equal final condition if there are no force applied. So as you can see here, if a group of body are exerting force on each other, that is interacting with each other, their total momentum remain conserved before and after the interaction, provided there is no external force acting on them. If there are no external force, then the momentum will conserved, means final momentum is equal to initial momentum. Okay, total momentum of both, here you can see total momentum of both object before collision equal to the momentum of both objects after collision. In the other word, total momentum of the two balls remain unchanged or conserved provided no other external force acts. This is known as law of conservation of motion. Now the theory of this chapter is ended.